hell am I? Or this wireless thing. I'm hoping anyway. The trials. So hard. Okay, so we just left off looking at a whole bunch of, I don't know, the generation of sampling distributions in R. Okay, so this idea of we've got a population, we're taking samples, we do this a whole bunch of times to get an idea of what the sampling distribution looks like. And what we saw was that even when the population, so when the population was normal, and we took sampling distributions, the sampling distribution looked normal, just skinnier, okay? And what we saw, even when the population distribution was bimodal, we took samples, it ended up looking normal as well. And even when the population distribution was very skewed or things like that, it also started looking normal as well. Okay, maybe still exposing a little bit of skew. All right, so this is all summarized with what we call the central limit theorem. Central limit theorem says, given a population and this population has the defining features, given a population with mean equal to mu and standard deviation equal to sigma, okay. If we take samples from this population, take samples from this population of size n, and we look at the sampling distribution of y bar. Okay. What we will see is that the sampling distribution of y bar would be approximately normal with mean equal to mu and with standard deviation equal to sigma divided by the square root of n, as long as n is large enough. Okay. Oh, I should say if we take random samples. Okay. So if we take random samples from this population, random samples of size n, and we look at the sampling distribution of y bar, looking at the sample mean of all of those samples that we've taken. So basically what we did, what we simulated in RStudio, if we do that, then the distribution of y bar will be approximately normal as long as n is large enough, quote unquote large enough. Okay? And that normal distribution will have mean mu and standard deviation sigma over the square root of n. Okay? And we kind of got a taste of that when we were looking at the sampling distribution. That first time around when we took small samples, we saw the spread was large, and as the samples got larger and larger and larger, the spread got smaller. And we see that that's accounted for here when we look at the standard deviation. We're taking the population standard deviation sigma, and we're dividing it by the square root of n. So as n gets larger, this denominator gets bigger, and so we see the spread shrinking. Yes?
So when do you use that standard deviation versus just sigma?
So this is when we are dealing with the population, and this is when we are dealing with the sampling distribution. Okay. So if I said IQ scores follow a mean distribution, a normal distribution with mean 100 and standard deviation 16, I could ask, what's the probability that someone has an IQ over 120? Then you would use standard deviation 16, the population standard deviation, because I'm just talking about the population. If I'm trying a random person from the population, what's the probability that this person's IQ is over this score? But now I could say, let me take samples of size 10. What is the probability that the sample of 10 people has an average IQ over 110? Okay. Now we are dealing with a sampling distribution because I'm talking about a sample. Okay, so what does it mean for n to be large enough? Because we saw when n was small, it certainly wasn't normal looking. Okay, we had the thing that had 3 peaks and all of these funny things that didn't quite look normal. So how large does n have to be large enough? Okay. Well, it's a little bit of an arbitrary and vague answer, but this is what we have to say. So, if the population has a normal distribution, then any size n is large enough. So if the population has a normal distribution, so if we're talking about IQ scores or whatever it is, if the population is normal, then any size n, so samples of size 2 is big enough for us to use the normal, apply the central limit theorem. Okay. So any size n is large enough, I should write, for us to apply the central limit theorem. Okay? For all other distributions, so anything that's not normal, n needs to be larger. For all other distributions, n needs to be larger, okay? So in general, unimodal, symmetric, but not necessarily normal. Unimodal and symmetric small samples, okay. But then as you get skewed distributions, you need larger ones. Larger samples required. Rule of thumb, samples of size 30 is generally large enough for most situations. But as you get more and more non-symmetric, or more and more skewed, you will need even larger samples. So if you have a very skewed distribution, samples of size 30 will still probably not be large enough. But for most things that we encounter, at least in the life sciences field, samples of size 30 will be generally large enough. Okay, generally large enough for most situations. Distributions that are heavily skewed even larger samples. Okay, so that's what we have. And the other aspects that are important for us to apply the central limit theorem is that the samples must be selected randomly. Okay. Randomly and independently. And if you're sampling without replacement, which is generally most of the time, you don't want to sample too much because that will actually affect this independence condition. So independent means what happened before has no effect on what happens on other events. But if you take samples that are too large, it affects that condition. Okay, so just think of like a deck of cards. The very first card I draw, the probability of the card being red is 50% because there's 26 red cards and 26 black cards. But once I draw a red card, the probability of me drawing another red card is slightly different because now there's only 25 red cards and 26 black cards left in the deck. Okay? And we're saying when the samples are small, that change is negligible. We can ignore it. But if we're getting samples that are bigger and bigger, then what we've taken out in our sample will start to affect what remains in the population, or remains in the deck. Okay, so when sampling without replacement, do not sample over 10% of the population. So if you have a large population, you're probably not going to run into this problem. But if you have a smaller population, you want to make sure you're not sampling over 10% of it. Okay, so let's try an example here. So let's say IQ scores come from a normal distribution, mean 100, standard deviation 16. I can say, what is the probability that a random person has an IQ over 10? Okay, so that's 1. And then 2, we're going to say, take sample of 8 people what is the probability that the sample has a mean IQ over 10. Okay, go ahead and try this out. So just pay attention that in one of these situations you are dealing with a random sample, and so that changes what you're dealing with. You're going to have to look at the properties of the sampling distribution. How are you guys doing? Need another minute, or are we good? I'm sorry? Alright, I'll give you guys another minute. Okay. Let's take a look here. Alright, so number one, that is, I think, pretty straightforward. This is what we did on our normal distribution. distribution stuff, we just say z is equal to 110 minus 100 over 16. We get z is equal to 0.625. So you can round that to 0.63 or I guess 0.62. So I'm just going to round to z is equal to 0.63. If you round it down to 0.62, I guess that's okay. So then we look this up in the z table. And you can look up the area to the left of negative 0.63 and get 0.2643 directly. Or if you look up the area to the left of positive 0.63, you would get 0.7357. And then to get the area over 110, you would do 1 minus 0.7357. And you get 0.2643. Yes?
When you say that it has to be over 110, do we just go 111? But not only is that, if it's the what the company.
Yeah, so in this case, because we're dealing with the normal distribution and it's continuous, we're just going to look at 110. Okay? You would only look at 111 or something if you're dealing with a discrete random variable. Okay, but here we're saying it's normally distributed, so we're looking at a continuous one, so we're looking at 110. I guess the argument could be made that IQ scores are discrete because you only get reported in whole numbers, but we're just looking at 110. Yes?
So if you didn't do 1 minus 0.7357, what would the shortcut be?
You would look up negative 0.63,
Okay.
and the area to the left of negative 0.63 is equal to the area to the right of positive 0.63. Okay, that should have been okay, right? All right, and so this is the new stuff that we learned today, applying the central limit theorem. And so when we take a random sample of 8 people, this tells you, oh, I'm dealing with a sampling distribution now. So the sampling distribution of y bar then comes from a normal distribution, and the mean is equal to what? The mean is equal to 100, it's equal to mu, and the standard deviation is equal to sigma over the square root of n, so I'm going to do 16 divided by the square root of 8. Okay, so y bar comes from a normal distribution with mean 100 and standard deviation 16 over the square root of 8. So this is the application of the central limit theorem. Okay. And a sample of size 8 is big enough because the population itself is normal. So any size sample is big enough when the population is normal. Okay, so now that we have this, we would do z is equal to 110 minus 100, and whatever this comes out to be, I forget, it was like 5 point, or 4 point, I don't know, 5 point something, 5.65, 6?
None.
5.657, I'll just say that, okay? So that's my standard deviation, so my z is equal to I already forget. 1.7 something? 1.77? Is that right?
No.
Okay, so my z is equal to 1.77, and I'm looking for the area to the right. I can look at the area to the left of negative 1.77, or I can find the area to the left of positive 1.77 and do 1 minus that. Okay? Whatever method you choose, you will get 0.0384. Is that okay? Good? Alright. So if you see questions like this on the quiz next week, we would be okay? These are fair questions? Okay. Alright, so, well, I guess start this in your notes because you're going to see something that looks a lot like this. that is that on sampling distributions. Yes.
Can you just explain, why we don't, when we use the continuity, corrections?
So the continuity correction is used only when you are trying to approximate a discrete thing with a continuous thing. So that's why it's called the continuity correction, because you're approximating something discrete. So generally, like the binomial distribution, or there's other distributions where it can only take on whole number values. And you're trying to approximate that with something continuous, which can take on decimal values. That's the only time you would use the continuity correction. If you're just dealing with the normal distribution by itself, no continuity correction. Okay, if something says it's normally distributed, don't be adding plus 0.5 or minus 0.5 or anything like that. If you're dealing with the discrete distribution directly, the binomial distribution directly, don't do continuity corrections. The only time you use the continuity correction is if you are trying to approximate a discrete distribution, like the binomial distribution, with the normal distribution. And the only reason why we approximate discrete distributions with the normal is because the normal distribution is generally easier to deal with in terms of we've got these tables that are very handy, rather than having to do the actual computation involved for a discrete distribution. Okay. So that's that. Okay, so that's the only time you do the continuity correction. It says approximate the binomial with the normal. That's the only time. If it doesn't say, if you don't see the words approximate this with this thing, don't use the continuity correction. Okay. And I guess now would be a good time. When would we approximate the binomial with the normal? I guess when I tell you to, but no, it's when it's, I guess when n is very large in the binomial distribution. So in the binomial distribution, normally, we would just calculate binomial probabilities directly. We would do n choose j, p to the j, 1 minus p to the n minus j. Okay? We would use that formula, calculate these things directly. But if n is too big, and you have too many j's to worry about, then the normal approximation is useful. Okay? So if I said we're going to take a sample of 10 shells, and the probability of a shell being streaked is 0.6, what's the probability I get 3 or fewer streaked shells? You just calculate that directly. You would do n choose j when j is equal to 3, j is equal to 2, j is equal to 1, and j is equal to 0. 4 numbers. It's a little tedious, but we can do it. On the other hand, if I said I'm taking a random sample of 100 shells, and what's the probability that we get 30 or fewer shells, then that would involve j is equal to 30, j equal to 29, all the way down to j equals 0. That's too many for us to want to calculate, so then we would apply the normal approximation. And because we're approximating it, we would then use the continuity correction. Okay, is that okay? And I know the book does these funny things where it's like, use the normal approximation just for when, y is equal to 10, this one particular number, and you have to go from 9.5 to 10.5. Generally, we would never do that, okay? Generally, we would just go straight into calculating that thing directly, because you only have to do it once. You do 10, choose whatever, okay? So you would generally not do this 10.5 minus 9.5, because That's like two things to calculate, when if you use the binomial directly, you would just have one thing to calculate. Okay, so the book does something a little bit funny, but I guess it's just, I think they do it so you can see how the normal approximation comes out pretty close to the actual value itself. Okay, is that okay? All right, are we feeling okay about sampling distributions and the central limit theorem stuff? Okay, so the central limit theorem tells us that when we take random samples from a population and we look at the sampling distribution of y bar, or the sample mean, if we look at the sampling distribution of the sample mean, we can know that the sample mean follows a normal distribution, or is approximately normal, as long as those conditions are met, as long as n is large enough. Okay? So that's one thing we know from the central limit theorem. So we're going to apply that knowledge in our first case of inference. Okay, so this is, now we're entering chapter 6. And this is kind of our first introduction to inference, and we're going to be dealing with confidence intervals. Do you guys remember what I said, why we even bother studying statistics in the first place, first day of class? No, alright. I'll retry. Okay, so I said we can draw conclusions from limited data. Alright? So this is our first time we're going to, we've been learning all of this stuff about looking at data and probability and all of this stuff. Now we get to actually draw some conclusions from limited data. Okay? So this is our first, I guess, step into inference. Okay, so we will now draw conclusions from limited data. Okay, let's stop right there, and I'm going to pull aside and tell a story. I'm going to do a little illustration here. Okay. Let's say you see this picture on Instagram, or Snapchat, or whatever it is. Okay, we'll say Instagram because Snapchats disappear in after 10 seconds or whatever. All right, so this is it's a picture of, what is this? This is a little doggy. Okay, doggy going for a walk on a football field. We will say at the 30-yard line. But the caption says, I don't know, dog going for a walk, or dog walking. Where is the owner? Hashtag he's invisible. Okay, so we have an invisible owner giving this dog a walk. We want to know, where is the owner? All we see is that the dog, his neck, is located at the 30-yard line. Okay. So the owner is invisible. Okay. And there's also a leash, an elastic leash that is invisible. But we know some properties about this elastic leash and the behaviors of the dog, okay? So we know the dog doesn't like to pull too hard against the leash because it kind of chokes him. So we know that the behavior of the dog is that about 68% of the time, the dog will remain within 1 yard of the owner. And about 95% of the time, the dog remains within 2 yards of the owner. And about 99.7% of the time, dog is within 3 yards of the owner. Okay, so we know that much about the behavior of the dog and the properties of this elastic leash. Okay, so we see the dog at the 30-yard line. Can we say something about the location of the owner? Okay, what can we say about the owner then?
And 29, 31,
What's that?
between 29 and 31, right?
Maybe.
It says within 1 yard of the owner.
So the dog remains within 1 yard of the owner about 68% of the time. Okay? And the dog remains within 2 yards of the owner 95% of the time. And the dog remains within 3 yards of the owner 99.7% of the time. But it's also possible that for the dog to be farther than 3 yards away from the owner if the dog is really ambitious and wants to really investigate something. But most of the time, he's within 2 yards of the owner. Okay? Actually, most of the time, he's within 1 yard of the owner. So what can I say about the location of the owner?
Is that at least 1 yard apart?
Not at least. He could be right next to the dog.
You don't know the distance next to the 30. I guess a scale.
I'm not sure. I'm making... Take one, two.
He's
Okay. Huh?
probably within 3 yards,
Alright. Probably within 3 yards. Yeah.
most likely.
Most likely. Okay. So I'm going to write. So actually, I will make a statement. Okay. Because the thing is I don't know where the owner is, and the owner could be anywhere. Could be right next to the dog. Could be 3 yards away from the dog. Could the owner be 3.5 yards away from the dog?
Sure.
It's possible for the owner to be within 3.5 yards away from the dog. Is it likely for the owner to be 3.5 yards away from the dog?
Yeah.
No, because based on what we know about the dog, we know the dog doesn't generally go that far away from the owner very often. Sometimes, but not very often. So based on what I know about the dog, I can say, seeing that the dog is at the 30-yard line, I am 95% confident that the owner is between the 28 and 32-yard line. Does that sound okay? And I could say I'm only 68% confident, but I'm 68% confident that the owner is between the 29 and 31-yard line. Or I could say I'm 99.7% confident that the owner is between the 27 and 33-yard line. Okay? But we'll just go with this kind of 95% feels kind of good. So we're going to say I'm 95% confident that the owner is between the 28 and 32-yard line. Is it possible that the owner is outside of that zone? It's possible, but based on what we know about the dog, we would be kind of surprised if the owner was, say, at the 33-yard line, because that means this picture happened to be taken at one of those odd times when the dog chose to be more than 2 yards away from the owner. Okay, so I can say I am 95% confident that the owner is between the 28 and 32 yard lines. Okay. So I see where I'm going with this. Why did I pick 68, 95, 99, 7 for the behaviors of the dog?
Empirical rules?
Empirical rule, and empirical rule is based on the normal distribution, okay? And so this is, I don't know, so not an allegory, but it's similar to what we understand about sampling distributions and the population, okay? So what we know is that when we take a sample, and if we can apply the central limit theorem, we know that y bar comes from a normal distribution, and the mean of y bar is mu, the same as the population mean, okay? So what we want to know is, we're going to use this to say, if we take a random sample, okay, if we take a random sample, we can observe y bar. Okay. Generally, so earlier today when we were talking about sampling distributions, I said the population has this mean and this standard deviation. Generally, we don't know that about the population. We don't know the mean of the population. We don't know the standard deviation of the population because we can't observe the population directly. So we usually have no idea what the true mean of the population is, okay? We do not know mu, the true mean of the population. Okay. But by observing y bar, what can we say about mu? So this question, we can kind of get an idea of how to answer this by understanding with this dog story, okay? So we don't know where mu is. Mu, the population mean, is like the invisible owner in our picture. We don't know where the true population mean is located. What we do see is we see the location of the dog. We can observe the sample, the mean of a sample. We can take a sample and we can observe the mean of the sample. But we don't know if that sample mean is bigger than the population mean. We don't know if the sample mean is smaller than the population mean. But we do know from the central limit theorem that the sample mean, y bar, comes from a normal distribution, and that normal distribution is centered at mu, the population mean. And because it comes from a normal distribution, we know that 68% of the time, y bar is going to be within 1 standard deviation of mu. 95% of the time, y bar is within 2 standard deviations of mu. 99.7% of the time, it's within 3 standard deviations of mu. So even though we cannot observe mu directly, by observing y bar, we can make statements about where we believe mu is located. So, because we know the behavior of y bar from the central limit theorem, okay, we know y bar comes from a normal distribution centered at mu, okay, and standard deviation sigma over the square root of n. So by seeing y bar, we can get an idea of where mu is located. So with the owner, we could say I'm 95% confident that the owner is between 28 and 32. Okay. By observing y bar, I can say I'm 95% confident that mu is within 2 standard deviations of y bar. Does that sound about right?